All right, today we're going to look at a quick extension of roots. What we've learned about roots so far is we know what a square root is, right? We could all take the square root of 4 or the square root of 36. We could even simplify the square root of 8 and put it into simplest radical form, right? Let's just focus on the basic square roots for right now, the ones that have nice, pretty whole number answers, okay? When you're taking a square root, think about what your goal is. Well, your goal is to find out what number squared makes a square root. Yeah, math people aren't great at naming things. So it's a square root because you want to find what number squared equals 4. Well, 2 squared is 4, so my answer is 2. 6 squared is 36, so my answer is 6. But we actually do have roots other than square roots, okay? Those will typically look like this, okay, where n is going to be something called the index, okay? And this number is going to be a positive whole number, okay? One that's bigger than 2. It's going to be a 3, a 4, a 5, or a 6, and anything bigger than that, really. And this is just going to be some number, okay? The index is going to tell us what kind of root we have. So as an example, this problem, instead of being a square root, would be a cube root, okay? And it would be telling us, it would be asking us what number cubed gets us 8. That's basically what this is asking us. What number cubed equals 8? And the answer is 2 cubed equals 8, so my answer is 2. A 4 would be a fourth root, okay? And so this would be asking us what number raised to the 4th power gets us 81. Well, that's 3, okay? We're going to look at these roots. We're also going to look at how they are similar to exponents, and then we're going to be able to do just a handful of things with those, okay? So here are different rules for roots. Some of these are extremely important. Some of them you won't use as often, but I'm going to just try to explain in simple terms what each of these rules means. So the first rule basically means that you should get the same answer whether you do the exponent first and then the root, or whether you do the root first and then the exponent. You really should get the same answer there. Those are equal. Rule number 2 is actually a rule that you're familiar with, right? Like if we have the square root of 3 times the square root of 2, we are allowed to multiply those to get the square root of 6. This rule is saying that if you had the cube root, or 2 of the same root of 2 different numbers, you could multiply the numbers under the roots together as well, okay? The key is that that index number has to be the same. The next rule, rule number 3, is saying the exact same thing as rule number 2, but with division, okay? You are allowed to divide 2 numbers that are both under the same root. Rule number 4 is a little strange, and it actually comes from exponent rules. Basically what this rule is saying is if I have a 4th root of a 5th root of a number, we'll just say 10, I could change it into a single 20th root. Okay, basically the idea is that, and it's probably easier to see on your packet than it is on the screen, but that if you have 2 roots, one with an index of m, one with an n, to make them 1, you'd multiply those, okay? That rule we don't use a whole particular ton. Rules 5 and 6 we do, though, okay? So here, this is the idea that if you have an nth root and an n exponent, they cancel each other out. Rule 6 I've left blank because actually there are 2 different possible answers, okay? We actually should know that the square root of x squared is the absolute value of x. Okay, we know when the square is underneath the square root and we take the square root of it, we get an absolute value because the squaring will make it positive and then the square root will be positive, even if we started with a negative. Here's the weird difference, though. If we do the same thing with a cube root, we just get x. We don't get absolute value of x because this answer could be positive or it could be negative. So what we find is that the answer to this one is the absolute value of a or just a, depending on whether n is even or odd. Okay, so basically if our index is even and you're taking the root of a variable and you're getting a cancellation with an exponent, you need to use absolute values. If it's odd, you don't, and in fact you shouldn't. So what should we be able to do kind of with these rules, and what are some things that we should be able to do? Here's some basic simplification stuff using that last rule, okay? Try to answer all 4 of these, pause, and then come back. Okay, I'm hoping the number ones were very easy, a 5 and a 2 there. Number 2, kind of answered before, that's x. Number 3 should be the absolute value of x, because if x were negative, our answer would still turn out positive either way. So that absolute value symbol shows us that our answer is going to be positive. Again, because we had an even index of 6, we have to use absolute values there. Okay, so that's the big stuff you need to be able to do there. So here's the deal. As it turns out, roots are basically the same thing as fraction exponents, okay? So here's what I'm going to tell you. If we have a cube root of x, that is the same thing as x to the 1/3 power. Those mean exactly the same thing. The 5th root of y is the same thing as y to the 1/5. Okay, all of those things are exactly the same. There's really no difference. We could even throw an exponent into the mix. Okay, so we could have a 6th root of, let's go z this time, to the 5th. Okay, and the way that I would write this is I could write it as z to the 5/6. You see, so my exponent is the numerator of my fraction exponent, and my root is the denominator of my fraction exponent, okay? So you should be able to switch between those 2 different forms. So let's just try 2 quick problems. Try converting x to the 2/3 into root form, okay? So try writing it like this. And then try writing, let's actually make it kind of a tough one, the square root of x to the 5th. Try converting that into an exponent form, so writing it like this. Try doing both of those, pause, and then come back. Okay, I'm assuming you've paused and come back. Remember, our bottom number in that fraction exponent is our root, or our index. So it's the cube root of x squared. This one is a little bit tricky. I know my numerator is going to be a 5, but what's my denominator going to be? I don't see an index. Well, I have to know that when I don't see an index there, that it's a square root. So I'm kind of actually assuming that there's a 2 there. So it should be x to the 5/2. And the reason you want to be able to switch between both forms is so you can kind of work in either format when you are simplifying. Okay, so for example, let's take a peek at number 2, 27 to the 1/3 power. I like simplifying in exponent form because I think it's pretty easy. There's a really easy way to simplify this. Make a factor tree for 27, and I get 3 to the 3rd. Okay. So now I'm going to change the 27 to 3 to the 3rd. I'm going to keep my exponent a 1/3. Remember your rules for double exponents. Your rules for double exponents say multiply those exponents. So I'm going to do 3 times 1/3. 3 times 1/3 is 1. So my answer is 3 to the 1st, which is 3. Okay? I can do the same thing even if things get a little more complicated, like for the 36. So for 36, if I make a factor tree, I get 3 squared times 2 squared. Okay? And I've got an exponent of, it's really hard to see on my screen actually, but looks like that exponent is 3/2. I still multiply my exponents, so I'm going to do 2 times 3/2, but I'm going to distribute it to both those exponents. So I get 3 to the 3rd times 2 to the 3rd. And now you can just use your basic exponent evaluation rules to figure this out. This is 27. This is 8. And then I multiply those together, and I get 216. Okay, so that's an easy way that you can simplify it. If you're also more comfortable In root form, that's fine too. Like for number 1, we can do the cube root of 27 over 8. So this is really the same thing as taking the cube root of each of those individually. Okay, and when you're in root form, you're just thinking, okay, what number cubed gets me 27? Well, that's 3. What number cubed gets me 8? Well, that's 2. Okay? The only thing that gets a little bit tricky is the negative exponents, okay? All you're going to do when you have a negative exponent is you're going to do your answer as if it was a positive exponent and then take the reciprocal of the answer. You're going to flip the answer because that's what negative exponents do. Negative exponents are like division, so you're going to flip it. You're going to flip it around the other way. Okay. So like here's an example, number 5, 16 over 81. I'm gonna make a factor tree for both of those. It's 2 to the 4th over 3 to the 4th. This is to the negative 3/4 power. So I'm going to multiply, and I get 2 to the negative 3rd over 3 to the negative 3rd. Before you do anything, the way to turn those negative exponents into positive is, like I just said, just flip it around. If you flip it around, you switch the sign on your exponents. So I get 3 to the positive 3 over 2 to the positive 3. This makes 27 over 8. I would suggest trying the rest of these. Number 9 especially is maybe a little bit challenging, but they're all good problems to try. So give these problems a try and get them checked over with me at some point. So these are the big things that you need to be able to do with fraction exponents and with roots. So again, the big things are can you simplify some basic ones when the root and the exponent match? And can you simplify in either root form or exponent form? And can you switch between the two forms? Switching between the two forms is important too. So as long as you can do all those 3 things, you're in pretty good shape.